Welcome to the deep dive, where we sift through the sources you've shared, extract the most important insights, and, well, give you that shortcut to truly being well informed. Today, we're diving into something pretty fundamental to how we understand the world: the incredible power of scientific prediction. And we're not talking about guesswork or, crystal balls here.
No, not at all. What's truly fascinating about scientific predictions is that they aren't mere guesses. They are rigorous, testable statements, deeply grounded in established theory, robust mathematics, and meticulous observation.
Okay.
Think of them as the ultimate stress test for any scientific model. When a theory anticipates phenomena that are later confirmed, its credibility isn't just enhanced, it often fundamentally reshapes our understanding.
Right. So for this deep dive, our mission is kind of to explore how this remarkable predictive power has guided research, sparked technological innovation, and, well, fundamentally reshaped our understanding of the universe. These validated predictions aren't just historical footnotes. They're genuine milestones lighting the path of human knowledge.
And we're going on quite a journey, actually. We'll be touching on remarkable intellectual triumphs across vast fields, from astronomy and physics to chemistry, biology, cosmology, and even earth science.
Wow.
It's really a testament to the enduring value of curiosity, skepticism, and human ingenuity.
All right, with that foundation, let's really dig into some of the most striking examples of this foresight. And where better to begin than with the cosmos? Our understanding of gravity has repeatedly led to some, well, jaw-dropping discoveries. Let's start with the story of Neptune's discovery. Back in the 19th century, astronomers like John Couch Adams in England and Urbain Le Verrier in France, they noticed something peculiar about Uranus's orbit. It was behaving.
Oddly,
Yeah, there were these subtle, unexplained irregularities, little wobbles.
right?
And it's incredible, isn't it? Instead of just dismissing these anomalies, they applied Newton's laws of gravity with profound belief. They hypothesized that an unseen planet, a sort of gravitational tugger, had to be out there causing these wobbles.
And their mathematical calculations were so precise, they essentially drew an X on the sky, pinpointing where this new planet should be,
Just based on math. Wow.
just based on math.
And the validation was almost immediate, which must have been a truly exhilarating moment. Acting on Leverrier's prediction, Johann Galli and Heinrich d'Arrest at the Berlin Observatory found Neptune in 1846, almost exactly where it was predicted to be, like within a degree.
That's right, incredibly close.
So what was the profound impact of that discovery, beyond just finding a new planet?
Well, it was a watershed moment, absolutely. But more specifically, it wasn't just finding a new planet. It was the audacious statement that we could locate something entirely invisible solely by the subtle gravitational ripples it left on what we could see. It was a triumph of abstract mathematical thought guiding empirical discovery. It fundamentally demonstrated that the universe could be mapped and understood through pure theoretical physics. Set a whole new standard.
Amazing. So from one celestial puzzle to another, Mercury's orbital precession. This was a stubborn problem for Newtonian mechanics, right? Its innermost orbit was exhibiting this slow precession, a slight shift in its elliptical path that just couldn't be fully explained by Newton's laws or the pull of other known planets.
That certainly was a real head-scratcher.
Okay.
This anomaly puzzled astronomers for decades. Then, in 1915, Albert Einstein's general theory of relativity bursts onto the scene.
Okay.
It provided this revolutionary new framework for gravity, predicting precisely the extra precession observed in Mercury's orbit. If you think of gravity not as a force pulling objects, but as the very fabric of space and time bending around massive objects.
Like marbles on a rubber sheet.
Exactly like that analogy. Einstein's equations showed this warping accounted perfectly for Mercury's odd little dance.
And when astronomers compared Einstein's calculations to the existing data, a perfect match.
A perfect match. It must have been an absolutely stunning validation for Einstein, solidifying his revolutionary ideas.
Yeah, I bet.
Indeed. It was one of the first truly convincing triumphs of general relativity, showing its power to explain phenomena that classical physics simply could not. It really cemented Einstein's place as a truly revolutionary thinker.
And he wasn't done. His general theory of relativity also produced another bold prediction, that massive objects like the sun should actually bend the path of light passing near them, an effect we now call gravitational lensing.
Right. And the beauty of this prediction was its elegant testability. You could actually check it. This effect would be most observable during a total solar eclipse, you see, when the sun's intense glare is blocked, allowing those background stars to become visible.
Ah, okay. Makes sense.
So in 1919, Arthur Eddington led an expedition to the island of Principe. His team meticulously measured the apparent position of stars near the sun and confirmed that their light was deflected by exactly the amount Einstein predicted.
Exactly.
Exactly. And crucially, it was twice the value Newtonian physics would suggest. So it wasn't just bent, it was bent by the right amount, according to relativity.
Wow, that must have blown people away.
It absolutely did. This propelled Einstein to international fame and marked the birth of gravitational lensing as this powerful tool for probing the universe.
Incredible. Now, for a prediction that took a little more patience, like a century of it, in fact, gravitational waves.
Oh, yes. This is a striking example of scientific perseverance on an epic scale. Back in 1916, Einstein's equations predicted that accelerating massive objects, think colliding black holes or neutron stars, should generate ripples in the very fabric of spacetime itself.
Ripples in space-time.
Yeah, like dropping a stone into a pond sends out waves, but in this case, the pond is space and time.
Okay, I think I get that.
But for a century, these cosmic whispers remained undetected. Their effects were just too subtle for the technology of the time.
100 years is an incredibly long wait for a cosmic whisper to finally be heard.
It really is.
Yeah.
But then, in 2016, LIGO, the Laser Interferometer Gravitational Wave Observatory, finally did it.
They got it.
They made the first direct detection from a pair of merging black holes.
Amazing. What did that breakthrough open up for us?
It opened an entirely new window on the universe. It ushered in gravitational wave astronomy. Scientists can now literally listen to cosmic events that were previously invisible.
Listen. How?
Well, listen in the sense of detecting these vibrations in spacetime. It gives us profound insights into the most extreme phenomena in the cosmos. Things like the birth of black holes or the collisions of neutron stars, events that often don't emit much light we can see.
A whole new sense for exploring the universe.
Pretty much, yeah.
Okay, moving from the vastness of space to the incredibly small, let's turn our attention to the fundamental building blocks of the universe and its origins. And we absolutely have to talk about the Higgs boson.
Ah, yes, the Higgs. So back in the 1960s, Peter Higgs and other physicists proposed the existence of this particle. It was seen as a crucial missing piece of the Standard Model that's our best theory for fundamental particles and forces.
Right, the Standard Model.
And the Higgs was needed to explain a really basic question. Why do some fundamental particles have mass and others don't?
Huh. I never thought about why they have mass.
Well, the theory suggested they get it by interacting with a field, the Higgs field, and the Higgs boson is sort of the excitation of that field. But it remained hypothetical for nearly half a century, a tantalizing puzzle eluding detection.
Decades of searching, but then 2012, right, at CERN.
Exactly. Scientists at CERN's Large Hadron Collider finally announced the discovery of a new particle with properties matching the predicted Higgs boson.
Found it. What was the deeper significance of finally finding it?
Oh, it was immense. It completed the Standard Model, certainly, which was huge in itself. But more profoundly, it confirmed this idea that mass isn't necessarily intrinsic to particles. It's something they acquire by interacting with this omnipresent field.
Like wading through treacle gives you resistance.
Kind of like that, yeah. A spoon gains resistance moving through honey. So this crucial piece finally brought our fundamental understanding of the universe's mechanics into alignment. And it validated decades, literally decades, of theoretical work.
Amazing. Okay, from the smallest particles to the biggest bang, let's talk about the cosmic microwave background, the CMB.
Right. So in 1948, physicists like Ralph Alpher, Robert Herman, and George Gamow were thinking about the very early universe. They calculated that if the universe truly began in a hot, dense state, the Big Bang theory, then it shouldn't be completely cold and empty now. It should be filled with a faint background glow of microwave radiation, essentially relic heat left over from that early energetic phase.
Like the afterglow of the Big Bang.
Exactly, a predicted afterglow.
Right.
But for years, it was just a prediction, no direct observation.
Yeah, then.
Then, in 1965, Arno Penzias and Robert Wilson, who were radio astronomers working at Bell Labs, they serendipitously stumbled upon this persistent background noise in their antenna, a hiss they just couldn't get rid of, no matter where they pointed it.
Annoying static.
Very annoying static for them. But it turned out to be the long-predicted CMB. They'd accidentally found the echo of creation.
Wow. How significant was this accidental discovery for our understanding of the universe?
Oh, incredibly significant. It provided compelling, tangible evidence for the Big Bang theory. It wasn't just an idea anymore. Here was the radiation it predicted. It fundamentally reshaped modern cosmology and launched an era of precision measurements. Studying the tiny variations in the CMB tells us so much about the universe's age, composition, and evolution.
It's truly remarkable how a theoretical prediction about the dawn of time could be confirmed by, well, static.
It really is one of the great stories of science.
And, it's not just physics and cosmology that benefit from this predictive power. Let's shift gears a bit. Let's turn our attention to the precise world of chemistry and a truly foundational breakthrough, Mendeleev's periodic table.
Mendeleev, a classic example. In 1869, Dmitri Mendeleev organized the known elements based on their properties and atomic weights. But here's the genius part, as you said. He left deliberate gaps in his table.
He knew there were missing pieces.
He predicted not just that elements were missing, but he predicted the properties of these undiscovered elements, what they'd be like, their density, their melting point.
Based just on the patterns in his table.
Exactly. He predicted they should exist to complete the pattern he saw.
And did they?
They did. Over the subsequent decades, elements like gallium, scandium, and germanium were indeed discovered. And each one remarkably matched Mendeleev's predictions, sometimes down to surprising detail in their chemical behavior.
That's incredible foresight. What was the effect of this on chemistry?
Well, it didn't just confirm the periodic law, showing this deep underlying order to the elements. It also brilliantly guided chemists in their search for new elements. It told them what to look for. It profoundly shaped modern chemistry as we know it.
Really laid the groundwork. Okay, now let's pivot to life on Earth and how prediction has shaped our understanding of biology and, well, our own planet. First, a truly delightful story from the world of evolution. Darwin's orchid and moth.
Ah, yes, this is a wonderful one. So in 1862, Charles Darwin received an orchid from Madagascar and Gracchum sesquipedale. And this orchid had an extraordinarily long nectar spur, basically a very, very deep tube holding the nectar.
Like unusually long.
Ridiculously long, something like 11 or 12 inches.
Wow.
And Darwin, with his theory of natural selection fresh in his mind, immediately made a bold prediction. He said there must exist a pollinating insect, probably a moth, with an equally long proboscis, its tongue perfectly suited to reach that deep nectar.
He predicted a moth with a foot-long tongue.
Pretty much. He was essentially predicting a specific, intricate case of coevolution, where two species evolve in lockstep, responding to each other.
That's quite a prediction. Did they find it?
Well, not immediately. It took decades. But eventually, the moth Xanthopan morgani predicta was discovered. And sure enough, its tongue perfectly matched the orchid's floral architecture. It could reach the nectar, pollinating the flower in the process.
Amazing. Predicta even named for the prediction.
Exactly. A stunning real-world validation of Darwin's foresight. It beautifully proves the intricate codependent relationships that evolution can forge between species.
Yeah, it remains a classic example of how evolutionary theory can generate specific, testable predictions about the natural world, even for something as detailed as a moth's tongue.
Precisely.
Now, switching scale again, the ability to predict celestial events, that's been a measure of scientific sophistication for millennia, hasn't it? Think about solar eclipse prediction.
Oh, absolutely.
Thales of Miletus in ancient Greece is famously said to have predicted a solar eclipse way back in 585 BC. Astonished his contemporaries, apparently.
Right. And while the details are debated, it marks that shift towards rational explanations, away from pure myth. The dawn of rational astronomy, some say.
And then things got much more precise.
These certainly did. Fast forward centuries, and you have Edmund Halley, using Newton's newly developed laws of motion and gravity. Halley predicted the 1715 solar eclipse over England with unprecedented accuracy. People could actually go out and see it happen when he said it would.
Must have delighted the public.
It did. It really solidified the predictive power of Newtonian physics in the public mind. Then, of course, in the 20th century, Einstein's general relativity further refined eclipse predictions, allowing astronomers to test the very limits of gravitational theory, like with the light bending we discussed.
Yeah. So this whole progression, it really charts the journey of astronomy from maybe mystical speculation to precise, testable science.
Exactly. A clear line of progress based on predictive power.
Okay, and finally, a very timely example, one that impacts us all directly, climate change models.
Yes, a crucial one. In the 1980s, climate scientists like James Hansen and his colleagues were developing sophisticated computer models. These models aim to simulate the Earth's climate system and predict how it would respond to increasing greenhouse gas concentrations from human activity.
And what did they predict?
They predicted significant global warming, changes in weather patterns, sea level rise, essentially the kinds of impacts we are now observing.
So the predictions were made back then.
Yes, the fundamental predictions about the warming trend were made in the 80s, based on the physics of greenhouse gases and the outputs of these early, though complex, models.
And the validation.
Well, observational data from the 1990s and 2000s onwards, things like global temperature records, melting ice sheets, sea level measurements, confirmed these warming trends. The planet was warming, broadly speaking, in line with their forecasts.
Right.
This validation, based on rigorous scientific modeling and subsequent real-world observation, has been critical. It's informed international policy, driven efforts to reduce greenhouse gas emissions, and underscored the vital importance of predictive science in trying to safeguard the planet's future.
It really brings home the real-world consequences and importance of getting these predictions right.
Absolutely.
So if we try and connect all these dots, from the grand cosmic scale of Neptune and gravitational waves down to the intricacies of a moth's tongue and the future of our planet, what emerges about the enduring value of scientific foresight? We've seen this extraordinary breadth and depth across space, life, matter, global challenges, all rooted in the sources you shared.
Yeah, I think each example powerfully illustrates how these theory-driven predictions, which are always grounded in careful reasoning and empirical rigor, how they've anticipated and explained phenomena before they were even observed or sometimes even observable. And what's truly striking, I think, is that these stories also highlight the immense patience and perseverance often required.
Right, the century waiting for gravitational waves.
Exactly. Or decades for the Higgs or for Darwin's moth. It's not always instant gratification. Sometimes decades, even a century, pass between a bold prediction and its final confirmation.
Yet time and again, this scientific foresight has allowed humanity to peer beyond the veil of the unknown. It fuels incredible innovation, inspires discovery, and continually deepens our understanding of the cosmos. It's like a beacon, isn't it? Guiding our quest for knowledge.
It really is. And it reminds us that the universe, complex as it is, seems to be fundamentally intelligible. The secrets of nature can be revealed through persistent curiosity, creative thinking, and that disciplined inquiry.
So as we look to the future, the challenges and mysteries we face are huge, right? Things like the nature of dark matter and dark energy, the origins of life itself, the impacts of artificial intelligence, the threat of pandemics.
Absolutely. And these will undoubtedly demand even greater predictive power from our scientific endeavors. We'll need better models, better theories.
But the lessons of the past, the stories we've discussed today, they teach us that scientific foresight, when it's consistently backed by solid reasoning and empirical evidence, that remains our most powerful tool for navigating the unknown.
It certainly seems to be. And this raises, I think, an important question for you, our listener. Thinking about this patient work of prediction, testing, and confirmation, what wonders still await discovery? And perhaps more personally, what pressing problems will you see solved by scientific foresight in your lifetime?
That's a great thought to leave people with. Because these stories of predictions coming true, they aren't just milestones in the history of science. They're enduring reminders of the human spirit's remarkable capacity to imagine, to reason, and ultimately to reveal the hidden order of the universe. Thanks for joining us on this deep dive.